So, in the last class we looked at the differential equation that describes mass conservation, and that is because we wanted to express mechanics of fluids using a differential approach, and mass conservation is a fact that is associated with any system that we are going to deal with, and therefore, we expressed that fact as a partial differential equation. And when we did that, we basically had two variables in that system. One was density and the other was the velocity field. We also simplified the relation for a constant density and then derived the equation of an incompressible fluid as well. So, we are going to continue and so we are trying to talk about dynamics of fluids, and as far as dynamics of fluids are concerned, these things are moving, they are in motion, and therefore, the way they start moving is because you are applying some external force onto the system, and and the kind of fluid flow that is generated is a consequence of how much is the force that you are applying. So, what you are really looking for is some kind of a relation between the velocities that are generated and connect that to the force that you have applied. Now, for simple systems, like for example, if you are throwing a stone, you know how to write down the velocity of the stone at every point. You will actually write down the Newton's second law, which is nothing but force is equal to mass into acceleration. And if you know the force, you can calculate what is the acceleration, and therefore, you will know what is the velocity at any instant of time. So, we need something very similar, okay, a corresponding expression, but for fluid flow, and also we need to do it in an Eulerian frame, because we are going to look at velocity at every point in space and in time, and we want to talk about forces acting at a particular point and see what is the kind of velocities that are generated. So, that is what we are going to look at. Okay. So, we are going to derive now equation of linear momentum conservation. So, we are going to talk about how what is the law that is going to come about when we are going to talk about conservation of linear momentum, and we will proceed exactly the way that we did yesterday. We will first write down, we will first consider a control volume. Let us consider a control volume. Okay. So, that is a control volume, and let us say that we are going to fix it at the origin of our coordinate system. So, that is the coordinate system. So, we will choose x, y and z. Okay. So, this length is dx, that length is dy, and this length is dz. So, these are the three lengths, and what we are going to say is that the fluid actually has a density rho. So, rho is the density of the fluid, and rho is the density of the fluid, and let us say v is the velocity of the fluid. So, it is a velocity field, okay. So, which varies at x, y, z and time. And what we need to do now is that we will find out how much is the momentum that is going into the system and how much is the momentum that is going out of the system, and whatever is left out will give rise to the accumulation. So, just the we proceeded yesterday, we will actually talk about momentum in and out through each phase. So, let us mark, let us say the first phase that we are going to consider is what I have marked with red color. Okay. So, that is a phase that is perpendicular to the x direction and its area is dy dz. So, what is the momentum that is associated with the fluid? So, we need to get, let us say, momentum flux in through the x phase. So, that is going to be equal to rho times v. So, that is going to be the momentum density, okay, because its mass times velocity is your momentum. So, this is density is mass per unit volume. So, mass per unit volume times velocity is going to give you the momentum density and multiplied by u times dy dz. So, u times dy dz is going to be the flow rate. So, velocity times area is the flow rate. So, this is the flow rate times the momentum is the total momentum that is getting in through the phase dy by dz. And what will be the momentum that is out through the other phase, let us say the phase that I mark it as green. Okay. Again we can use the Taylor series expansion and say that the out momentum is going to be del by del x of rho v u times, or should really write it as rho v u times dy dz plus del by del x of rho v u times dx dy dz. Okay. So, that is rho. So, the first term, so we are expanding about the first term and then writing down what is the momentum that is going out. So, similarly we can do it for each phase. So, let us do that. So, let us say phase momentum flux in, momentum flux out, and the difference which is in minus out. So, as far as the x phase is concerned, we just calculated that the momentum in is rho v times u into dy dz. The momentum out is rho v u plus del by del x of rho v u dx times dy dz, and therefore, the difference is minus del by del x of rho v u times dy dz. Okay, here we have multiplied it with u because u is the velocity component of velocity that is in the x direction. Now, we can do the same thing for the y phase. So, let us look at the y phase now. So, the y phase is the momentum that is entering from the bottom and then the momentum that is going above from the top. So, similar calculation. So, it is going to be rho v is the momentum density times the flow rate in the upward y direction, which is v times dx dz. Out will be rho v times v plus del by del y of rho v times dy into dx dz. and therefore the difference is minus del by del y of rho v v times dx dy dz dx, and in the z direction it's going to be rho v times w into dx dy, and out would be rho v w plus del by del z of rho v w dz times dx dy, and therefore the difference would be minus del by del z of rho v w dx dy dz. Okay. So, this is the quantity that is interesting to us, because that tells you what is the momentum in minus momentum out, and the momentum in minus momentum out should be equal to the rate of change of momentum in that particular volume. So, if there is in is not equal to out, that means the momentum of the fluid in that particular volume is going to be changed, and we know how to do that. So, we can say that in minus out has to be equal to rate of change of momentum, okay, which I can write as del by del t of rho v times dx dy dz. So, rho is the density, rho times dx dy dz will give you the mass, mass times v will give you the momentum, and del by del t is therefore the rate of change of momentum. So, rate of change of momentum must be then equal to the parts that I have marked in that red box. But then if you think about it a little more seriously, what you know is that the momentum or the rate of change of momentum is not just because there is a difference in the momentum in minus momentum out. You can get a rate of change of momentum if you apply a force also, right. So, for example, if something is moving with a certain momentum and if you apply a force, you are actually going to change its momentum. So, the rate of change of momentum is not just equal to in minus out, it actually has to be also equal to the total forces acting on that fluid element. Okay. So, therefore, the right equation is sum of forces plus momentum in minus momentum out has to be equal to the total rate of change of momentum. So, therefore, we find that our equation should really be sum of forces that is acting plus all the quantities that we have found out as in this red box. So, I will write that down. So, it is minus del by del x of rho v u times dx dy dz minus del by del y of rho v v times dx dy dz minus del by del z of rho v w dx dy dz is equal to del by del t of rho v times dx dy dz. Okay, so, that is the expression that now we have gotten when we have said that the sum of the forces plus momentum in minus momentum out is equal to rate of change of momentum. And now, we need to simplify this expression. So, I will write that as sum of f is equal to del by del t of rho v, and I will bring all these quantities into the right hand side plus del by del x of rho v u plus del by del y of rho v v plus del by del Z of rho V W times dx dy dz. So, that is what you get when you rearrange. Now, this expression can be further simplified, and we get that when we are going to apply the product rule. So, let us apply the product rule throughout. So, the first term is density times rho v by rho dou t plus rho times plus del rho by del t times v, plus the next quantity that I can write as rho v so I'll put rho and u together. Okay, so del by del x of rho u times v plus del v by del x times rho u. So, that is just the product rule of this particular term, okay, and so on, plus del by del y of rho v times v plus rho v times del v by del y, plus the last term del by del z of rho w plus rho times v plus rho w into del v by del z times dx dy dz. Is equal to, let us mark some of the terms that we want to write together. Let us say that term del rho by del t into v, that term and this term, and so we will write them together. And other term, so okay, let us write del rho by del t plus del by del x of rho u plus del by del y of rho v plus del by del z of rho w times v. So, those are the terms that I have used in red, plus other terms rho times dou v by dou t plus rho u times dou v by dou x plus rho v times dou v by dou y plus rho w times rho v by dou z. Okay, so these are the terms that are in underlined as red in the above expression and other terms. Now, what is this term in this square bracket that I have put? That is nothing but continuity equation. So, if you look at your notes, it is essentially del rho by del t plus divergence of rho v, okay, and we know that that quantity is actually equal to 0. So, for this term does not exist, and only term that we end up is equal to rho times dou v by dou t plus u dou v by dou x plus v dou v by dou y plus w dou v by dou z. Okay. So, that is nothing but the total derivative, the material derivative of velocity which we had shown. So, that is nothing but is equal to rho times dou v by dou t plus v dot grad v. So, that is a nicer way to write it if you like, and that is equal to what is on the left hand side? On the left hand side it is basically the total force. So, I will write that is equal to total force acting. Oh, of course, I forgot a dx dy dz, that is multiplying the. Okay. So, that is where we have ended up with. So, now we need to talk about the forces acting on the fluid element. The forces can be actually two types. Okay. One is called body forces and the other is called surface forces. So, when I say body forces, okay, it is an external force that acts on the entire or the force that depends on the volume of the fluid element that you are looking at, and you know one such force, for example gravity. Okay, gravity depends upon what is the amount of the fluid that you are looking at, and here it is obvious that if I take dx dy dz to the left hand side, I really need what is the force density or the force acting per unit volume, and the force acting per unit volume is nothing but rho times g. Okay. So, the really the force is m times g, but if you are talking about the force per unit volume, it is rho times g. Okay. So, rho g is the force that is going to come up as a body force. Now, surface forces are the force that acts on the surfaces, okay, of the fluid element. So, if you have, let us say, let us look at the same fluid element, I will make another diagram. Okay. So, that is a fluid element and we had it as x, y, which is different coordinate system, x, y, z. Okay. Now, on any face of it, let us say this fluid element is part of the fluid, this fluid element is surrounded by other fluid elements. So, the other fluid elements basically will be exerting some forces on this fluid element as well, and that force is exerted on the surface of this fluid element. So, what I am trying to say is that let us say if that is one of the fluid element, above that, draw again. Okay. So, that is one. Then above it there is going to be another fluid element, then on the side there is going to be another fluid element and so on. So, the red fluid is going to exert some force on the black fluid, the black fluid is going to exert some force on the green fluid. So, this is all forces exerted on the surface, not on the that force exerted is essentially proportional to the surface area, because that force is getting transferred across the area. Okay. So, those are the kind of forces that you call as surface forces, and there are two surface forces. One is something that you already know, and that is the pressure. The second is the shear stress. So, if you remember the definition of the Newton's law of viscosity, we defined it as stress is equal to a constant times strain, okay, and that constant is what we called as viscosity. So, stress is again defined as force per unit area. So, the pressure forces, shear stresses are examples of surface forces. Okay, because you can see that that force is defined per unit area, unlike the body force which is defined per unit volume, because it depends upon the mass of the object that is under consideration. So, since we now understand what are the body forces and what are the surface forces. So, as far as body force is concerned, we know what is the expression that we need to use in the equation that we have. So, this is the form of the equation at the moment. This is the form of the equation at the moment. Okay. So, the left hand side we have simply written it as total forces, but we need to be more explicit about it. So, rho g is the body force contribution that is going to go into the sum of F, and then we need to find out what is the form of surface forces that should go in the expression for capital F.